Today I'm going to be discussing exploring for helium. The talk will fall into 4 parts. We'll have an introduction, then we'll talk about the play elements that are required to produce, migrate and trap the helium. We'll talk about 4 case studies, and then we'll finish off with some conclusions. So helium is found in large amounts in minerals of uranium and thorium. And these emit alpha particles as they decay, which generates around 3,000 metric tons of helium per year throughout the lithosphere. And we can see in the diagram here is a uranium-238 atom, and it undergoes fission, but it also undergoes radiogenic decay, and it's that decay which yields the helium. Now, helium is very rare because it cannot be retained by the Earth's gravitational field. And so we only find around 5.2 parts per million in the atmosphere. And it's also very hard to contain because it's got such a small atomic size, it can pretty much leak through anything. So you have around 40 days of storage before it's all gone. Helium behaves a lot like hydrocarbons, such as natural gas, and cannot be made artificially. And much of the world's helium has been produced as a byproduct of the extraction of natural gas in the American Southwest. So all producing helium reserves were discovered by accident. And currently the price of helium is around $100 per 1,000 cubic feet. So what are the required elements for successful helium plays? Well, we know from hydrocarbons that you need 5 play elements to create a working hydrocarbon system. And these are the reservoir, the seal, the source rock, the trap, and suitable migration and timing. And the source rock viability also depends on the burial temperatures and depths. So we can adapt these play elements for helium prospect generation. And the facts to consider are: how and where is the helium generated? How is the helium released from source rocks? What are the migration pathways? How does helium accumulate and remain contained in a reservoir? And how can traps be compromised? And there are clear differences between hydrocarbons and helium at almost every stage of this process. So if we have a look at the table here, we can see that for the source rock, in a petroleum system, you need organic matter. In a helium system, you need uranium decay. As far as maturation goes, you need burial and heating in a petroleum system, but you really need a large volume of stable crust for a long time to generate enough helium. In terms of migration, it's the kerogen maturing that drives the fluids through the system, whereas in a helium system, you need to heat the helium to a sufficient level where it can escape from minerals. In terms of the accumulation, you just need a mud rock, cap rock in a petroleum system, but you need something finer grained typically to store the helium beneath. And then as far as trap integrity goes, it's pretty similar for both systems. So if we look at this diagram here, this is just showing the elements of a typical commercial helium trap. And the most important elements here are the source rock, which typically is basement rocks, but could also theoretically be Paleozoic rocks. And then we need a suitable cap rock here, which is usually an anhydrite or a salt, because these are the only caps that typically have a fine enough grain size to retain the helium within your reservoir. So let's talk about the sources of helium, and as we mentioned earlier, it's radiogenically sourced from alpha decay of either uranium or thorium. And typically it's sourced from basement rocks and cratons of Proterozoic and Archean age. So these can be up to 3.8 billion years in age. Predominantly these rocks are metamorphic or granitic in character, although you can also see cyanites, and they have to contain uranium and thorium. And typically they're impermeable, these rocks, so you need to have fracture systems to act as migration pathways for the helium to escape from these rocks. And often groundwater is a conduit, and it can be charged due to the proximity to the faults cutting through the basement, and then it can migrate upwards. But then we can also have more modern sediments, less than 1.8 billion years old, which can contain uranium and thorium, but are more time constrained. And these are typically some sedimentary ore deposits or reservoirs, which may be proximal to uranium ore bodies, or may even contain uranium and thorium, something like pitchblende. And they can yield helium that then migrates into stagnant pore waters, and it will gradually partition into a gas phase. And I've just put some examples here of typical fractured basements. So these are from the Rona Ridge west of Shetland, but almost any fractured basement, if it has sufficient radiogenic qualities, could act as a helium source. In terms of the maturation, concentrations of helium will naturally increase in the subsurface over time, as long as you have something like this uranium yellow cake we see here in the subsurface, which gradually decays, releasing the helium. And continental cratons may act as closed systems which allow the helium to accumulate over billions of years, and then finally you just need a way to release that helium through fracturing and increases in temperature. And the helium can actually be trapped in zircons, apatites or titanites, which are typically inaccessible at shallower depths. So what happens is that you see we have a helium atom here which is moving through the crystal lattice, and energy is added to that atom by collision or through heating of the crystal. And normally it's through heating. And if enough energy is added, the helium can then be bumped and gradually move through the crystal lattice, and it will either stop when the energy level drops below the activation energy, or if it manages to escape from the crystal lattice. So the primary migration involves migration out of the source rock initially and out of the original host minerals. So we've already said that it needs to be bumped and have that activation energy. And when uranium undergoes this fission, the fission products create tracks within the material, these fission tracks. And you can see in here you need just the right conditions with the right degree of decay, and in that case you are actually going to create these fission tracks, and the helium can move through the fission tracks to escape. But either of these processes, these two forms of migration, they both require an increase in temperature. And one example of this is in Yellowstone, where we have this giant hotspot sitting beneath Yellowstone, and that temperature is actually generating helium, which we see in places like Grand Prismatic Spring today. And these helium concentrations are low because we haven't got a lot of time that's happened to allow the accumulation of helium through time, but nonetheless we are seeing helium being produced as a result of this higher temperatures. Typically speaking, the migration process is facilitated by groundwater and the movement of fluids through the rock. So let's talk a little bit about nitrogen and helium, and we commonly see an association between nitrogen and helium. And what you tend to see is that nitrogen concentrations increase away from volcanoes while carbon dioxide concentrations decrease. And the reason why you see more nitrogen may be due to hydrocarbon stripping during migration. But it's very important because high nitrogen concentrations are a flag that there may be economic helium reserves as well. And the correlation between high nitrogen and high helium is around 0.939 as that correlation ratio. So there's a very high degree of correlation. And I've just got an example here from Iran where you've got the Kabiaku field, which is around 220 kilometer long anticline, and 85% of the fill is nitrogen, and we're also seeing helium in there as well. And the first US discovery of subsurface helium was at Dexter in 1903, and this is a model of the helium plant, showing the helium plant here. And what we see in this example is that was 82.7% nitrogen and 1.64% of helium. And typically speaking, as a rule of thumb, you need to look for values of above about 0.3% helium to have the likelihood that they may be economic. So high nitrogen concentrations are a flag that there may be economic helium reserves. And it's funny that helium is also a proxy for potential uranium exploration and uranium reserves. So once we've had the initial migration out of the crystal lattice, then you need secondary migration as well. And what you often find is that helium and nitrogen are found together with carbon dioxide and methane. And this suggests that the same processes are operating and may facilitate helium trapping. And the secondary migration will either occur through free gas migration, so gas just migrating through the pore spaces, or more typically through the movement of groundwater with dissolved helium and nitrogen. And what happens is that eventually what you'll see is that you'll get stripping of these gases from the groundwater due to the migration of more carbon dioxide and methane. So the carbon dioxide and methane will continue to be dissolved, and that will lead to exsolving of the nitrogen and helium. And the example I've shown here is from South Africa, and we're going to come back to this as one of our case studies, but you can see the network of faults here which are permitting the migration of these groundwater through these conduits. So we've said already that helium and nitrogen are often found together with carbon dioxide and methane, and when that groundwater with the dissolved contents is equilibrated with carbon dioxide and methane, the insoluble helium and nitrogen will exsolve. And so once they've migrated into a gas trapping structure, the balance between the supply and the seal efficiency will determine whether or not you build up helium reserves. So what you really need is tiny pore throats to act as a seal because of the very small atomic radius of the helium, and then that seal will allow the helium to become trapped beneath usually halite or anhydrite. And we have some examples here from Iran, from the Gash Saran formation. So these evaporites here are around 700 meters in thickness, and these would provide a suitable cap rock for helium reserves. And we see these same rocks in Qatar where they are actually trapping helium. And then I've also put this diagram in here showing the Guarani Aquifer in South America, which is the world's second largest aquifer. And this transports helium from basement rocks into the atmosphere. And what we see is that the aquifer is hosted in these Triassic Aeolian sandstones. And wherever you see a Cretaceous basaltic seal over the top, the helium is trapped. But everywhere else, the helium is allowed to escape to the atmosphere. So let's have a look at some case studies now. And we'll begin by looking at the geology of the Western Panhandle field. And this huge network of gas fields sitting in here, which is the Hugoton field and the Panhandle field here, was used as part of the Federal Helium Reserve up until it was disbanded earlier this year. And what we see in this example is that we have a northwest trending anticline. This is the anticlinal structure sitting in here. And underneath it, we have this Cambrian to Precambrian igneous basement. And the basement is composed of granite, rhyolite, and diabase. And the granite is highly radioactive. And then we also have some sedimentary rocks which are radioactive, which include this granite wash here. And the granite wash, which is basically weathered basement, also acts as a potential source of helium. And what we find is that there's uranium-bearing asphaltite in the granite wash, and then there's helium in these rocks as well. And the helium is migrating up through fractures that are associated with this anticline, and then they're becoming trapped beneath these middle Permian evaporites. So the helium sources for the Panhandle field are from two basins. So they're mainly from the Palo Duro Basin, which is sitting down in here. And this helium is derived from the basement rocks, and around 75% of the helium within the Panhandle field is generated by these rocks. And then 25% of the helium is derived from low helium concentrations in large volumes of hydrocarbon gas in the Anadarko Basin, sitting up here towards the northeast. And this helium is sourced from traces of uranium in Paleozoic hydrocarbon source rocks. So there's two different sources for the helium within the Panhandle uplift. And it's interesting to note that there are 6 natural gas reservoirs in the United States contain 97% of the identified US helium reserves. So you can see these fields that are sitting in here. They are from a variety of states, but each of them is responsible for a vast amount of the helium that's produced in the US. Our second case study here is from New Mexico. And helium has been produced from 8 fields in the Four Corners area since 1943. So that Four Corners is at the junction of 4 of the states in the southwest US. And you can see here that 950 million cubic feet of helium has been produced from Devonian and Triassic reservoirs. And the helium content is up to 5%. And the hydrocarbon gases are relatively low, with the remainder being made up of nitrogen. So this shows once again this association between helium and nitrogen. And it's actually very important that the hydrocarbon gases make up a lower percentage, because this makes it much easier to get the helium out, and it means that the helium concentrations are typically higher. So the production economics of these fields here are driven by helium. So it's not a case of producing the natural gas with helium as a byproduct. It's the helium which is driving the economics. And what we see is that the values are fairly high in Devonian Triassic reservoirs, but once you get up into the Cretaceous reservoirs, you have lower helium values and higher hydrocarbon gas values instead. So that's not so economic. And what we see here is these beautiful orthogonal fault networks sitting in here, and these offset Precambrian basement, and they also act as migration pathways. So they allow the helium to migrate up from the basement into these Devonian and Triassic reservoirs. And once again, the helium is originated from the decay of uranium and thorium in Precambrian granites, with lower Permian evaporites acting as seals. And we can see here, this is a map of the helium fields, and some of these are oil and gas fields which contain helium, and some of these are pure helium fields as well. Our third case study I mentioned earlier on in the talk, and this is helium from the Free State in South Africa. And what we're seeing here is that we have these Precambrian Witwatersrand deposits, these conglomerate deposits which are around 2.9 billion years in age. And this is a section through one of these conglomerates, and what we see is the conglomerates are made up dominantly of quartzite pebbles here, and the matrix is also quartzite, which is an excellent seal to retain any potential helium within these rocks. And then they also host minor amounts of uranium, pyrite, fly speck carbon, and gold. And this is actually that you can see there's a little gold grain here in this section, so there's an individual gold grain there as well. So obviously most of the production is concentrated on gold, and in fact this area in the Free State has produced around 5% of all the gold ever mined worldwide. But recently, from 2016, a new helium plant opened up in this area to produce the helium which comes from uranium and is dissolved in groundwater. So what happens is that the uranium is decaying, the helium is produced here, and the groundwater is running through this system up the faults and then moving towards the surface. So Lind, the company, they are actually mining the groundwater and producing the helium, which is around 2 to 4%, up to 11% from the gas within this within the groundwaters. And it's unclear as to whether the methane is actually being generated from Karoo sediments, which overlie the Precambrian rocks, or whether it's actually being generated from this Witwatersrand. And maybe some of this carbon here, the fly speck carbon, is providing a source for this methane. So in terms of location, we're sitting down here in the Free State. Johannesburg is up here, and this is where the gold industry started in South Africa, and this is the Witwatersrand Basin. So we're around 300 kilometers to the southwest of Johannesburg. And this is what the section looks like. So we've got these older rocks here. These are the Precambrian rocks, around 2.9 billion years old, overlain by lavas, which provide a very nice seal. Then these lavas are also of a similar age. And then overlying that, we have the Karoo supergroup. And then what's happening is that these shafts here, which are originally for mining gold, have been repurposed to produce some of this groundwater. And they're also drilling new wells in the area to access the groundwater. This is an example of one of these wells. And you can see that the estimated content here, a P50, is around 106 BCF of helium, which is not to be sniffed at. It's definitely economic. So finally, we're going to look at Alberta. And there are various approaches that you can use for exploration. We've talked about the different play elements. So first of all, you can use a play-based approach. So what do you need? You need uranium-bearing granites that can decompose into helium. So if we look at our map of this area, here is Alberta sitting in here, and here is Saskatchewan sitting just to the east. And we can see that there's quite a lot of granite sitting here in the subsurface, which has been mapped out. So that the decay of that granite would definitely provide helium. We also need an evaporitic seal, and then this is a map of a working tight seal running through from Saskatchewan into Alberta. So we have that second element here. And thirdly, we need some migration pathways, hopefully leading into working gas fields. And in this case, it seems obvious that when the helium is migrating up into these gas fields, that would be a good target if you're already producing the gas. So we have these different play elements, the source, the seal, and the reservoir, and if you combine these together on a play-based exploration map, we have our sweet spot in the middle here, and that's where all of these combine. So we have quite a large target area there where you might be drilling with the hopes of finding some helium. So that's one approach. But there's a second approach, which is a more data-based approach, and this is where you interpolate a helium concentration map. So we've got 800,000 wells, and we used 180,000 of them that had helium values to create this map. So this is literally a helium contour map. And you can see that we've got helium over 0.2%, over 0.4%, and then this red area here is over 0.9%. So we've got values in there which are relatively high in helium and should really be considered as economic. So this provides an excellent lead map, and I'm just going to zoom in on two of these areas to show you what they might look like. So this is the first area here in Seal. This is further to the north, and Seal it's famous for producing oil sands, but it also has potential for helium reserves. We can see two wells that were drilled in here at around 0.3% helium. So that's definitely a potential reservoir hosted in Devonian sediments which underlie the oil sands, and it's that unconformity with the overlying oil sands that makes this play prospective. And then the second example here is right down in the corner, the bottom eastern corner of Alberta, where the city of Medicine Hat has been drilling some exploration wells in helium, and Vile is planning to open a cryo hub facility in the city at some point as well. So we can see that there's some values here up to 5.9% helium. So this would definitely be economic, and there are definitely plans for more exploration in this area by Vile and other companies. And this extends over into the Swift Current area in Saskatchewan, where Second Wave Petroleum and others are already producing helium. So just to move to some conclusions, the key exploration components is an area of ancient crust with radioactive minerals or old clastic sediments. You need a stable geological history to allow the helium to accumulate, and then a later tectonic event to facilitate the helium release. So you really need heating and ideally pressure to allow the helium to escape from the crystal lattice, and then also to migrate through fracture pathways into shallower sediments. And then you need some secondary migration to trap via gas stripping or from groundwater. And viable traps to allow the helium to accumulate, hopefully with excellent seals. So I've just put an example here showing from the Diné Bikaya field in Arizona, where we have radioactive fractured sills sitting down here and dense limestone and seal as a shale. So once again, this demonstrates these play elements in action. And the best places really to find helium? Well, I would suggest looking for old sediments with stagnant pore waters, areas with saline and cool, shallow traps, and this helps the helium to degas from fluids at relatively low pressures. At the end of long migration pathways, which will maximize the gas exposure to helium-bearing waters, and away from supercharged or thermally mature hydrocarbon systems, because that means that you won't be diluting your helium as much. So something like granite wash, shallow fractured basement rocks, and then very tight capping rocks should be what you're looking for. So I'm going to leave it there, and I'm happy to take any questions. Thank you.